Hey guys, welcome back to the second video of section 2.3 on inverses. So we talked about having a 2 by 2 or 3 by 3 and finding the inverse. There's actually a really cool fast way on how to find the inverse if it's a 2 by 2 matrix. What we want to do is imagine we had this matrix A that had these elements A, C, B, D, right? So A, B, C, D. Then A has an inverse for sure, right? If A times D minus B times C doesn't equal 0. If it equals 0, then there is no inverse. So that's really great. Okay, so that's your first thing. So the second thing is A times D minus B times C is something called a determinant, which you're going to learn in chapter 3. And the way we find an inverse is as follows. We're going to first do 1 divided by the determinant, which is AD minus BC. Then we're going to take the D and the A and we're going to swap them. And then we are going to take the B and the C and we're going to negate them. So with that being said, you can find the matrix, the inverse of a matrix that way. How amazing is that? Think about it for a second. Somebody figured this out. So we're going to do, in this example, 3 times 2 is 6, minus negative 1 times negative 2 is 2. 6 minus 2 is 4. So I'm going to do 1/4. And now, guys, what I'm going to do is I'm going to, let's pick a different color. I'm going to swap these two around. And then I'm going to negate these two. So 1/4 of 2 is a half. 1/4 of 1 is a fourth. 1/4 of 2 is a half. 1/4 of 3 is 3/4. This is your inverse and you are done. How insane is that? So that's how you do a 2 by 2. So another thing that's extremely important are the properties of inverses. Okay, so if we know A has an inverse, okay, and K is greater than 0, right? It's a positive integer, and C is a scalar that's not 0, then all of these values have inverses. So the inverse of A has an inverse, okay. A to the K, which means like A squared, A to the third, A to the fourth, has an inverse. A scalar times A has an inverse, and A transposed also has an inverse. Some of these are easy to prove, like the first one. So all I did was I took each element here, or each piece here, and I just wrote to the -1 for inverse. See that? What is -1, -1? +1, right? If you take the inverse of an inverse, you get back the original. Sure, we said A had an inverse. We know from the properties from the last section, you can swap these, right? So this one's a little bit tricky. C is a number. C to the -1 is 1/C, right? 2 to the -1 is 1/2. 3 to the -1 is 1/3, and so on. And then that's just the inverse. And then again, the transpose, you could just find the inverse and transpose it. So we can, if you take a look at, the second one, for example, A to the K, if you take a look at A to the K and take the inverse of it, and A inverse K, they match or they're going to be equal. So that's something really nice, and we can show it here in 2 different ways. So imagine taking A to the -2. We can rewrite it as A squared to the -1, or we can write A to the -1 squared. In other words, the inverse squared. Well, I did this out for you guys here. A squared is A. We're going to multiply those out. If you multiply those out, guys, we're going to get A times A to be 3, 5, 10, 18. You can pause the video and confirm it, but we do this by like this times this, right? 1 times 1 is 1, 1 times 2 is 2, 1 plus 2 makes 3, and so on. So just assume that you're with me. A times A is A squared, and you get 3, 5, 10, 18. How do we find the inverse for a 2 by 2 matrix? Oh, I just showed you a really fast way. So all you have to do is find the determinant. That's 54 minus 50. 1 over 4. And then we're going to swap these two, 3 and 18. And then we're going to negate the 5 and 10 to be negative 5 and negative 10. And so then you just take 1/4 of all of this. So in this case, I did A squared, and then I found the inverse. Or you can take A, find the inverse first by doing the determinant. That's going to be this, swapping 1 and 4, and negating 1 and negative 1 and 2 to negative 1, negative 2. Figuring this out, now you have A to the negative 1. You want to square it, which means write it twice. So it's this times this, and I promise you that it will give you this, okay? So those are important, and this is one of my most important here as well. A times B inverse, look how amazing this is equal to B inverse times A inverse. We know multiplication is not always commutative, but in this case, A times B inverse is B inverse A inverse. And my final thing here is if C is an invertible matrix, meaning it has an inverse, then the following are true. This is insane. If A times C is equal to B times C, then A and B are the same. And if C times A equals C times B, then A times B is the same. What you notice here is one of them is on the right and the other one's on the left. So I'm going to just show you or prove to you one of them, and then you'll just get the, whatever you do to every single time with matrices, whatever you do on one of them, you have to put it exactly where you, so if I put a C to the negative 1 here, I'm not allowed to put it in the front here. So if you put on the right side here, you must put on the right side here. Okay? So I'm going to put it on the right side there. I'm going to put it on the right side there. A matrix times its inverse disappears. Right? And you're done. So that's pretty much how you do it. And then you do the left side. And so this is going to be very important for later. So remember that AB to the negative 1 is B to the negative 1, A to the negative 1, and this right and left cancellation. Okay, I'm going to do the next and final video on systems of equations. So I'm going to do that as our third and final video for section 2.3. So I hope everything makes sense so far.